So now we want to calculate, in this exercise, the distance between two planes, two given planes. And before we start, there are two situations to consider, because we have to define what's the distance between two planes. In fact, it's going to be the shortest distance you can get between 2 points, to any 2 points on the plane. Now, situation one is this: you've got two planes that are not parallel, and if they're not parallel, they're going to intersect each other, right? Because they stretch out in all directions. They're going to meet possibly along a line like this. So in this situation, if you can pick this point that's both part of each plane, so the distance between a point and itself is 0. So here I've got a distance of 0. So we're gonna have to figure out, before doing anything, if we have parallel or non-parallel planes. If we have parallel planes, okay, this is the worst. Let me rewrite this. I don't know why it's so small. I think I know why. Situation 2. Parallel planes. So, okay. In that case, if you take a point here, the point that's the closest on the other plane will be such that the line or joining these 2 points will be at a right angle with each plane. Okay. And this is going to be the distance. And it's the same distance no matter what pair of points you take, as long as the line joining them forms a right angle with the 2 planes. Okay. So this needs to be a right angle, and this needs to be a right angle here as well. So it's going to be the same distance. So that's the first thing to look at. Do we have parallel planes or not? And how do we know this? I'm trying to think about this, like, especially with our example here. I've got this plane and that plane. Using those numbers, how would I figure out if they're parallel or not? Think about this, pause, and come back. Now, here's the thing. If I have a plane, I can easily get a normal vector to that plane. If I've got another plane that's parallel, it could have another normal vector, maybe longer, maybe shorter, or longer, maybe way longer, maybe not even pointing in the same direction. But let's say this is N1 and N2. If you have parallel planes, the normal vectors will also be parallel. So N1 and N2 are going to be parallel in this situation if you have parallel planes. So I'm in situation number 2. And if they're parallel, that means that N1 is proportional to N2. Proportional, I wrote proportion, but I wanted to write proportional to N2, which means that N1 is a multiple of N2. That's how you can detect if 2 vectors are parallel. So we can start with this. With our problem, we could look at the normal vectors for each plane are, and those are easy to get. I'll have 2 of them, right? N1 and 2. Let's look at the first plane. First plane is its equation is x minus y plus 2 equals 4. So N1 is 1 minus 1, 2. So 1 minus 1, 2. 1 minus 1, 2. The other plane, minus 3, 3, minus 6. Minus 3, 3, minus 6. I remind you that it's important that all your variables are on the same side of the equation so that you can collect the coefficients of x, y, and z in order to get the normal vectors. Now, the question is n2 a multiple of n1. It's not hard to see that minus 3 n1 is actually equal to n2, so they are parallel, since n1 and n2 are proportional, we could say parallel, the planes are parallel. Okay. Oh, maybe just going back up again, in situation number 2, I could actually have, there's a sub-situation where you have parallel planes, but you have identical planes. So we can look at this here, like, do we have identical planes? We have identical planes if both equations are identical. Now they may not look identical, but they're identical in the sense that they have the same solution, and we need to check. We could check this. You see, this plane, this equation here, the coefficients minus 3, 3, and minus 6. I can get them by multiplying throughout by minus 3 the left-hand side. But if I do this, if I multiply by minus 3, I have to multiply by minus 3 on the other side, and I would get minus 12 if I do that. But here I have 3, so those would be identical planes if that coefficient there would be minus 12. If the 3 would be a minus 12, instead of 3, the two planes would be identical planes, and the distance would be 0. Okay. If we don't notice this, it's not a big deal, because as we solve this problem, if we get a distance of 0, we'll just say, oh, we didn't notice, but those were two identical planes. So it's not a big deal if we don't notice this, but I just wanted to tell you. And it's not going to happen here. Actually, I picked two planes that are parallel, but not identical. So we're going to get a positive distance. So how do I do this? I need 2 points, right? So right now I know I have two parallel planes. It's always nice to draw a little diagram to understand what you're really doing. I need to pick 2 points on each plane, and when I'm going to, well, 2 points. Yeah, we didn't discuss how we're going to solve this, but it's in order to find the distance between two planes, it's really simple. It's going to be exactly the same as finding the distance between any point on one plane and the other plane. So let's say this is a point on the first plane. I just need to calculate the distance between A and the other plane. So it's harder to choose the other plane. I always have students choosing the same plane, and then they get a distance of 0, and then they're not surprised. Okay, so I need to choose the other plane, and our method. Remember, we're going to choose some random point on the other plane, join those to form a vector. We're going to take vector n that's perpendicular to both planes, actually. So n could be n1 or n2 actually, but I mean, if we technically this is n2 in the sense that it's the one we can easily obtain by looking at the second plane. But whether you choose n1 or n2 doesn't matter, because they're both parallel vectors, and we're going to project this vector onto n2 in order to get in order to calculate its norm and find the distance. Okay, so let you do that on your own, actually, or maybe we can choose all the same points. So I need to choose a point on the first plane. So here's what I've chose. You see, this is the first plane here. So again, you can try to be lazy. If you replace y by 0, z by 0. You solve for x, you get x is 4, so you get 4, 0, 0 is the first plane. A 4, 0, 0 is a point on the first plane. And I need B, which is a point on the second plane. What could I do? I could just use the exact same strategy. Replace I could replace xy by 0, solve for z, and we get minus 2. Did I do this right? 400. Yes, yeah, 400 and 00 minus 2. Oh, sorry, not quite. If I do 00, it's not going to be minus 2. Let's be well, if I replace by 0, I get minus 6z is 3, so z would be actually be a fraction. I don't like fractions, so I'll it would work, but make our life a bit harder. So instead I will replace y by 0, z by 0, and then minus 3x is 3, so x is minus 1. So minus 1, 0, 0. That I like better. You see, so you can, I always like to work with integers. It's a lot easier, so I recommend that you do the same. So now calculate your distance, since you've got everything now in hand. So pause and come back. Here you go. This is my solution. So you'll notice I used the shortcut that I talked about before. I didn't calculate actually the projection completely. I calculated the norm directly of the projection. Ultimately I got this. If you stop there, that's fine. I don't mind. But notice that in 54 there's a perfect square. There's 9. Which is a perfect square, so I can pull out the 9, and then it becomes a 3, and then 3 and 15 can simplify, and that's why it simplifies to 5 over root 6. But whether you write 15 over root 54 or 5 over root 6, in this course, I don't mind whether you simplify that or not. But ultimately, I mean, you should be able to simplify this. I know that there's a question coming up, which is, those of you reading the book, you'll notice that there's a formula for finding a distance between a point and a plane, or even a point on a line in the book. I don't care that much about the formula. It's useless in the sense that you're never gonna have to do this, calculate this manually, the distance between a point and a plane, point and a line. And what's important here is really the concept of projection. So this is why I'm forcing you to calculate your distances using projections, because I want you to remember what a projection is like. Because by the end of the course, we might see actually an application of projections, and if we don't understand what a projection is anymore, and we just remembered formulas, that's the concept of projection is going to be useless to us. So I want you to be able to calculate all of your distances by doing a projection. Okay, and that's it for section 3.3.